Welcome to DAR Tutors. Today, we're going to explore quadratic functions. This topic is essential for your IB mathematics applications and interpretation higher-level studies. By the end of this video, you will be able to, first, identify and define a quadratic function and its graph, a parabola. Second, convert between three different forms of a quadratic function to easily find key features like the vertex and intercepts. Third, use the discriminant to determine the number of x-intercepts. And finally, solve various types of IB-style problems involving quadratic functions. We'll begin with a real-world problem. Imagine an energy-conscious person, Misha, wants to heat his coffee using solar energy. He decides to build a reflecting surface. He knows that sun's rays arrive parallel and that they will reflect off the surface according to a specific law. This is the law of reflection. The angle of incidence equals the angle of reflection. This means the angle at which a ray hits the surface is identical to the angle at which it bounces off. The goal is to design a surface that can focus all of these parallel rays onto a single point where the cup is placed. This problem leads us to our first key question. What geometric shape will focus parallel rays to a single point? The answer is a parabola, which is the graph of a quadratic function. This is a powerful example of how pure mathematics, specifically the properties of quadratic functions, can solve practical engineering problems. It shows us that parabolas are not just abstract curves, but have a fundamental role in the physical world, from solar reflectors to bridges and satellite dishes. To understand parabolas more deeply, let's look at how they can be created. We are entering the world of conic sections. The term conic section refers to a family of curves that are formed by intersecting a double inverted cone with a plane. A double inverted cone is formed by placing two right circular cones, which have their apex directly above the center of the base, one upside down on the other. If we pass a flat plane through this three-dimensional shape, the two-dimensional curve that results is a conic section. Depending on the angle of the plane relative to the cone, we can produce several different shapes: a circle, an ellipse, a hyperbola, and what we are most interested in, a parabola. A circle is formed when the plane cuts horizontally. An ellipse is a slightly tilted cut that doesn't go all the way through. A hyperbola is formed by a vertical plane that cuts through both cones. But how do we get a parabola? A parabola is the intersection that occurs when the plane is parallel to the cone's slant edge. This specific cut produces the unique curve we call a parabola. This geometric definition is the foundation for the algebraic definition we will be studying. Let's now define a quadratic function algebraically. You will be able to recognize and work with the general form of a quadratic function. A quadratic function is a mathematical relationship between two variables, x and y, that can be written in this general form. Y equals x squared plus bx plus c. The coefficients a, b, and c are constants. The crucial condition is that a cannot be 0. If a were 0, the x squared term would vanish, and the function would become linear, not quadratic. The values of a, b, and c determine the specific characteristics of the parabola, such as its width, direction, and position. Our first objective is to understand how to determine if a specific point lies on the graph of a quadratic function. A point, xy, satisfies a function if, when you substitute its x-coordinate into the function's equation, you get its y-coordinate. Let's work through an example. Consider the function y equals 3x squared plus 2x. We want to know if the point 2, 16 is on this graph. To check, we substitute the x value 2 into the function. This gives us y equals 3 times 2 squared plus 2 times 2. We then calculate this value. 2 squared is 4, so we have 3 times 4, which is 12, and 2 times 2 is 4. Adding them together, we get y equals 16. Since our calculated y value is 16, which matches the y-coordinate of the point 2, 16, we can confirm that this point satisfies the function. In other words, the point 2, 16 lies on the graph of y equals 3x squared plus 2x. Now let's try another one. Does the point source 3, 1 satisfy the function y equals negative x squared minus 2x plus 1? We apply the same process. Substitute x equals negative 3 into the function and evaluate. Substituting x equals negative 3, we get y equals negative of negative 3 squared minus 2 times negative 3 plus 1. Careful with the signs here. -3 squared is 9, so the first term becomes -9. -2 times -3 is +6. And we have +1. Adding these values, we find that y equals -2 to 2. The calculated y value of -2 does not match the y coordinate of our point, which was 1. Therefore, the point, 3, 1, does not satisfy the function. It does not lie on the graph. So, we've now seen how to confirm if a point is on the graph of a quadratic function by direct substitution and comparison of the y coordinates. Our next objective is to find the x values that correspond to a given y value. This is a fundamental skill in solving quadratic equations. When we substitute a specific value for y into a quadratic function, we transform it into a quadratic equation. Solving this equation gives us the x-coordinates of the point or points on the parabola that have that y value. A quadratic equation can have 0, 1, or 2 real solutions for x, corresponding to a graph that does not intersect the horizontal line at that y value, touches it at one point, or cuts through it at 2 distinct points. Let's work through an example. Consider the function y equals x squared minus 2x plus 3. We want to find the x values when y equals 2. We substitute 2 for y, which gives us the equation 2 equals x squared minus 2x plus 3. To solve this, we rearrange it into the standard form x squared plus bx plus c equals 0. Subtracting 2 from both sides, we get x squared minus 2x plus 1 equals 0. You might recognize this as a perfect square trinomial, which can be factored as the quantity x minus 1 all squared. Setting this equal to 0 gives us one solution, x equals 1. This means the point 1, 2 is the only point on the parabola y equals x squared minus 2x plus 3 with a y coordinate of 2. Now let's find the x values for a different y value. What are the x values when y equals 18 for the same function, y equals x squared minus 2x plus 3? Again, we substitute 18 for y, giving us the equation 18 equals x squared minus 2x plus 3. Rearranging, we get x squared minus 2x minus 15 equals 0. This is a standard quadratic equation. We can solve this by factoring. We look for two numbers that multiply to -15 and add to -2. Those numbers are 3 and -5. So the equation factors to the quantity x minus 5 times the quantity x plus 3 equals 0. This yields two solutions. X equals 5, or x equals -3. This tells us that the parabola intersects the horizontal line y equals 18 at 2 points, 3, 18, and 5, 18. So, we've now seen how to use substitution to turn a quadratic function into a quadratic equation, and how to solve it to find the x values for a given y value. Now let's delve into the geometry of these functions. Our objective is to understand the key features of the graph of a quadratic function, which is called a parabola. We can get a feel for the shape by plotting the simplest quadratic function, y equals x squared. We can build a table of values. For example, when x is 3, y is 9. When x is 2, y is 4. When x is 0, y is 0. Notice the symmetry. When x is 2, y is also 4. When we plot these points and draw a smooth curve through them, we get this shape, which is a parabola. Let's define its key components. First, we have the vertex. This is the single lowest or highest point on the graph. It's where the parabola turns. For y equals x squared, the vertex is at the origin, 0, 0. Second, the axis of symmetry is the vertical line that passes through the vertex. It divides the parabola into two mirror image halves. For y equals x squared, the y-axis, or the line x equals 0, is the axis of symmetry. The y-intercept is simply where the graph crosses the y-axis. You can always find this by setting x to 0 in the function's equation. The x-intercepts are where the graph crosses the x-axis. These are the values of x that make y equal to 0. They are also known as the roots of the quadratic equation x squared plus bx plus c equals 0. A parabola can have 2, 1, or 0 x-intercepts. So, to summarize, the key features of any parabola are its vertex, axis of symmetry, y-intercept, and any x-intercepts. Now let's explore different forms of quadratic functions. Our objective here is to understand the properties of the factored form, i.e. equals a times the quantity x minus p times the quantity x minus q. This form is particularly useful for quickly identifying the x-intercepts of the parabola. Let's consider the general equation, equals a times x minus p times x minus q. To find the x-intercepts, we need to find the x values where y is 0. So we set the function equal to 0. By the null factor law, if the product of these factors is 0, at least one of the factors must be 0. So either x minus p equals 0, which means x equals p, or x minus q equals 0, which means x equals q. Therefore, the x-intercepts of a quadratic in this form are simply p and q. Remember, the axis of symmetry is always midway between the two x-intercepts. So we can find the equation of the axis of symmetry by taking the average of the intercepts. X equals p plus q all over 2. The vertex will have this same x-coordinate. The value of a in the equation tells us two things. If a is positive, the parabola opens upwards and is said to be concave up. If a is negative, it opens downwards and is concave down. Also, the absolute value of a determines the width. A larger absolute value of a makes the parabola narrower. A value of a between -1 and 1 makes it wider. Let's summarize. The factored form y equals a times x minus p times x minus q gives us the x-intercepts at p and q, the axis of symmetry at their midpoint, and the direction and width of the parabola from the coefficient a. Let's put this into practice with an example. We will sketch the graph using axes-intercepts and state the equation of the axis of symmetry. Our function is y equals 2 times the quantity x plus 3 times the quantity x minus 1. Comparing this to the form y equals a times x minus p times x minus q, we can see that a equals 2. Since a is positive, the parabola opens upwards. This is a crucial piece of information. Next, let's find the x-intercepts. From our form, we know the intercepts are at x equals p and x equals q. In our equation, x plus 3 is the same as x minus -3. So p is -3 and q is 1. The x-intercepts are at -3 and 1. These are the points where our parabola crosses the x-axis. Now let's find the y-intercept. To find the y-intercept, we always set x equal to 0. Substituting 0 into our equation, we get y equals 2 times 3 times -1, which equals -6. The y-intercept is at 0, or 6. Finally, we need the axis of symmetry and the vertex. The axis of symmetry is x equals the average of our x-intercepts. That's x equals the quantity -3 plus 1 divided by 2. This simplifies to x equals -yin. The vertex must lie on this line. To find the y-coordinate of the vertex, we substitute x equals 1 into the original equation. Y equals 2 times -2, which is -8. So the vertex is at 1, 8. We now have all the information to draw our sketch. It opens upwards, passes through, 3 thus, 1 thus, and 0 to 6, and has a vertex at 1, 8. First, we draw our axes. Next, we plot the intercepts and the vertex. Then we draw the axis of symmetry. Finally, we draw the parabola passing through these points. Let's look at a special case of the factored form, the vertex form. You will be able to interpret and graph quadratic functions in the form y equals a times x minus h all squared. This form arises when a parabola touches the x-axis at exactly one point. This happens when the x-intercepts p and q are the same. So, if p equals q, we can replace both with h. The factored form becomes y equals a times x minus h times x minus h, which simplifies to y equals a times the quantity x minus h squared. This is often called the vertex form because the vertex is easily found. Let's look at an example. Sketch y equals 1/2 times the quantity x plus 2 squared. Here a equals 1/2. Since it's positive, the parabola opens upwards. And h equals -2 because x plus 2 is the same as x minus -2. This tells us the parabola touches the x-axis at the single point x equals -2. This single point is the vertex. So, The vertex is at ∑2, 0. The axis of symmetry is the vertical line through the vertex, which is x equals -2. The y-intercept is found by setting x to 0. This gives us y equals 1/2 times 4, which is 2. So the y-intercept is at 0, 2. Now we can sketch the graph. It's an upward opening parabola that touches the x-axis at 2 and crosses the y-axis at 2. This vertex form is particularly efficient for sketching parabolas that touch the x-axis. We've explored the general form, y equals ax squared plus bx plus cc, and the factored form, y equals a times x minus p times x minus q. Let's introduce another key form, the completed square form. Our objective is to understand the completed square form, also known as the vertex form, which is written as y equals a times the quantity x minus h squared plus k. This form is highly valuable because it tells us the coordinates of the vertex directly. In the completed square form, the vertex of the parabola is located at the point with coordinates, hk. Be careful with the sign here. The x-coordinate of the vertex is positive h. The axis of symmetry is the vertical line, x equals h. Let's apply this to an example. Sketch y equals -2 times the quantity x plus 1 squared plus 4. We will use the vertex, axis of symmetry, and y-intercept. First, the vertex. Our equation is y equals -2 times x minus -1 squared plus 4. So h is -1 and k is 4. The vertex is at 1, 4. The axis of symmetry is x equals -1. What about the direction the parabola opens? We look at a. Here, a is -2, which is less than 0. This means the parabola opens downwards. Finally, we find the y-intercept by setting x to 0. This gives us y equals -2 times 1 squared plus 4, which is -2 plus 4, or 2. The y-intercept is at 0, 2. Now we can sketch the graph. It's a downward opening parabola with its highest point, the vertex, at 1, 4, and it crosses the y-axis at 2. So we've successfully sketched a parabola by directly reading the vertex and direction from its completed square form. So far, we've graphed parabolas from the factored or completed square forms. But what if we're given the general form, e equals ax squared plus bx plus c? One powerful technique to analyze and graph from the general form is to convert it to the completed square form. This process is called completing the square. Let's work through an example. Convert y equals x squared plus 4x plus 3 to the completed square form and find its vertex. The first step is to focus on the x squared and x terms. We need to find a number to add to these terms to create a perfect square trinomial. The formula for the number needed is the quantity b over 2 squared. Here b is 4, so we need to add 4 over 2 squared, which is 2 squared, or 4. To keep the equation balanced, if we add 4, we must also subtract 4. So we get y equals x squared plus 4x plus 4 plus 3 minus 4. The terms x squared plus 4x plus 4 form our perfect square, which factors as x plus 2 squared, and 3 minus 4 is -1. So the completed square form is y equals the quantity x plus 2 squared minus 1. Now that it's in completed square form, finding the vertex is easy. Comparing this to y equals a times x minus h squared plus k, we see h is -2 and k is -1. The vertex is at +2, 1. The axis of symmetry is x equals 2. A is 1, which is positive, so it opens upwards. The y-intercept is found by setting x to 0, which gives y equals 3. We have converted the quadratic and found all its key features. What if the coefficient of x squared a is not 1? Let's tackle that case next. Our objective is to complete the square when a is not equal to 1. The process is similar, but requires one extra step at the beginning. Let's work with the quadratic y equals 3x squared minus 4x plus 1. The first step is to factor out the coefficient a, which is 3, from the x squared and x terms. This leaves us with 3 times the quantity x squared minus 4 over 3x plus 1. Now, we focus on completing the square inside the brackets. Our new b is -4 over 3. The number to add is -4 over 3 divided by 2, all squared, which is -2 over 3 squared, or 4 over 9. We add 4 over 9 inside the brackets. But we must also subtract it to keep the expression equivalent. This gives us 3 times the quantity x squared minus 4 over 3 as plus 4 over 9, plus 1 over 3 minus 4 over 9. The first 3 terms in the bracket are now a perfect square. The quantity x minus 2 over 3 squared. The remaining constants, 1 over 3 minus 4 over 9, combine to negative 1 over 9. Finally, we distribute the 3 back through the brackets. 3 times the quantity x minus 2 over 3 squared minus 1 over 3. And that is our completed square form. The vertex is at 2/3, negative 1/3. Since a is 3, which is positive, the parabola opens upwards. The y-intercept is 1. We have successfully completed the square with a coefficient a not equal to 1, a key skill for more complex problems. So, we've seen how to use the completed square form, but what if we want to sketch a quadratic directly from the general form? Y equals x squared plus bx plus c without converting first? Our next objective will show you how to do this efficiently. We will learn to sketch a quadratic from its general form, I equals x squared plus bx plus c. To do this, we need a shortcut for finding the axis of symmetry. We know the axis of symmetry passes through the vertex and is exactly midway between the x-intercepts. We also know from the quadratic formula that the x-intercepts are given by x equals negative b plus or minus the square root of the discriminant, all over 2a. The midpoint of these two values is just their average. The plus and minus discriminant parts cancel out, leaving us with x equals negative b over 2a. This is a very important formula. The axis of symmetry, and therefore the x-coordinate of the vertex, is always negative b over 2a. Let's summarize the steps. First, find the axis of symmetry using x equals negative b over 2a. Second, substitute this x value into the function to find the y-coordinate of the vertex. Third, state the y-intercept, which is just the constant c. Fourth, find the x-intercepts by solving the quadratic equation x squared plus bx plus c equals 0. You can factor or use the quadratic formula. Finally, use all this information to sketch the graph. Let's apply this method to an example. Our objective is to sketch a parabola using the negative b over 2a formula. Consider the quadratic y equals 2x squared plus 8x minus 10. First, let's identify our coefficients. A equals 2, b equals 8, and c equals negative 10. Because a is 2, which is greater than 0, we know the parabola will open upwards. This is a great first check. Now let's find the axis of symmetry. Using the formula x equals negative b over 2a, we substitute the values of b and a. X equals negative 8 over 2 times 2, which is negative 8 over 4, or negative 2. So the axis of symmetry is x equals negative 2. Next, the vertex. The x-coordinate of the vertex is 2. To find the y-coordinate, we substitute x equals 2 into the original function. This gives y equals 2 times negative 2 squared plus 8 times negative 2 minus 10. Calculating this, we find y equals 8 minus 16 minus 10, which is negative 18. The vertex is at the point char 2 to 18. What about the y-intercept? The y-intercept is simply the constant term c, which is negative 10. The y-intercept is at the point 0 to 10. And finally, the x-intercepts. To find the x-intercepts, we set y equal to 0. We need to solve the equation 2x squared plus 8x minus 10 equals 0. Notice that all coefficients are divisible by 2, so we can factor out a 2. This gives 2 times the quantity x squared plus 4x minus 5 equals 0. The quadratic in the bracket factors to x plus 5 times x minus 1. Setting each factor to 0 gives us x equals 5 or x equals 1. The x-intercepts are at 5, 0, and 1, 0. We now have all the pieces to draw an accurate sketch. We have an upward opening parabola with its vertex at on 2 and 18, a y-intercept at 0 or 10, and x-intercepts at 5, 0, and 1, 0. The axis of symmetry is the line x equals 2. This systematic approach ensures an accurate sketch every time. We have reached the 10-minute mark. If you find this lesson helpful and are looking for expert personalized tuition, please contact DAR Tutors. We offer specialized support for IB, A-level, and IGCSE curricula. We have seen that a quadratic can have 2, 1, or no x-intercepts. Our next objective is to use a powerful tool, the discriminant, to determine the number of x-intercepts without graphing or solving the full equation. The key here is the quadratic formula, which solves the equation x squared plus bx plus c equals 0. The number of solutions, and thus the number of x-intercepts, depends entirely on the value of the expression inside the square root, b squared minus 4ac. This expression is called the discriminant, and we often denote it with a delta d. Let's analyze the 3 possible cases based on the value of the discriminant. First, if the discriminant b squared minus 4ac is greater than 0, its square root is a positive real number. The quadratic formula will give us 2 distinct x-intercepts. The parabola will cross the x-axis twice. Second, if the discriminant is exactly 0, its square root is 0. The plus-minus part of the quadratic formula vanishes, leaving us with only one solution for x. The parabola will touch the x-axis at a single point, which is also its vertex. Third, if the discriminant is less than 0, its square root is an imaginary number. There are no real solutions for x. The parabola does not intersect the x-axis at all. This means it either lies entirely above the x-axis or entirely below it. This discriminant delta is a powerful tool. Without doing any heavy calculation or drawing, we can immediately understand the fundamental relationship between a quadratic's graph and the x-axis. Let's work through an example to see how to use the discriminant to determine the number of x-intercepts. Our objective is to determine the relationship between the graph of a quadratic function and the x-axis. Consider the function y equals x squared plus 3x plus 4. Our first step is to identify a, b, and c. Here a equals 1, b equals 3, and c equals 4. The next step is to calculate the discriminant. The discriminant, delta, is b squared minus 4ac. Substituting our values, we get delta equals 3 squared minus 4 times 1 times 4. This is 9 minus 16, which equals negative 7. Since the discriminant is negative, what does that tell us about the x-intercepts? A negative discriminant means there are no real solutions to the equation x squared plus bx plus c equals 0. Geometrically, this means the graph does not intersect the x-axis. It either lies entirely above it or entirely below it. To know which, we look at the coefficient a. Since a equals 1, which is positive, the parabola opens upwards. An upward opening parabola that doesn't touch the x-axis must lie entirely above it. We call such a quadratic positive definite. This means y is greater than 0 for all real values of x. So, we've analyzed the quadratic using only a and the discriminant to understand its position relative to the x-axis. Let's quickly review the concepts of positive and negative definite quadratics. Our objective is to clearly define and identify these special cases. A quadratic function y equals x squared plus bx plus c is called positive definite if its y value is positive for all real values of x. It never touches or crosses the x-axis, and it's always above it. The conditions for this are that a must be positive, so it opens upwards, and the discriminant must be negative, so it doesn't intersect the x-axis. Conversely, a quadratic is called negative definite if its y value is negative for all real values of x. It's always below the x-axis. The conditions for this are that a must be negative, so it opens downwards, and the discriminant must be negative, so it doesn't intersect the x-axis. These definitions are important for solving inequalities and for understanding the global behavior of quadratic functions. We can also use the discriminant to solve problems involving unknown coefficients. Our objective is to determine the range of values for a constant k that cause a quadratic to intersect the x-axis in a specific way. Let's work through this classic IB problem. For the function y equals x squared minus 6x plus k, we need to find the values of k for which the graph cuts the x-axis twice, touches the x-axis, or misses the x-axis completely. The key to this problem is the discriminant. Let's find it first in terms of k. For our function, a equals 1, b equals 6, and c equals k. The discriminant, delta, is b squared minus 4ac. Substituting these values, we get delta equals negative 6 to squared minus 4 times 1 times k. This simplifies to 36 minus 4k. Now we can analyze the three cases. Case A. To cut the x-axis twice, the discriminant must be greater than 0. So 36 minus 4k must be greater than 0. Rearranging this inequality, we get 36 is greater than 4k, or k is less than 9. For the parabola to cut the x-axis twice, the value of k must be less than 9. Case B. To touch the x-axis, the discriminant must be equal to 0. So 36 minus 4k equals 0. Solving for k, we find that k equals 9. When k is exactly 9, the parabola will touch the x-axis at its vertex. Case C. To miss the x-axis, the discriminant must be less than 0. So 36 minus 4k is less than 0. Rearranging, we get 36 is less than 4k, or k is greater than 9. If k is greater than 9, the parabola will not intersect the x-axis at all. We have now used the discriminant as an algebraic tool to determine the geometric properties of a parabola based on an unknown coefficient. We've spent a lot of time analyzing quadratic functions given their equation. But what if the situation is reversed? Our objective now is to find the equation of a quadratic if we are given its graph or key information about it. This is a common IB problem type, and there are a few standard approaches based on the information provided. Our objective is to find the equation of a quadratic when we know its x-intercepts. We'll find the equation of a downward opening parabola. Here we have the graph of a parabola. It's concave down, and its x-intercepts are at x equals 1 and x equals 3. Since we have the x-intercepts, we should use the factored form, y equals a times x minus p times x minus q. Our intercepts are p equals r1 and q equals 3. Substituting these values, we get y equals a times the quantity x plus 1 times the quantity x minus 3. All that's left is to find the value of a. To find a, we need one other point from the graph. The graph clearly shows a y-intercept at 0, 3. We can use this point. Substituting x equals 0 and y equals 3 into our equation, we get 3 equals a times 1 times negative 3, which simplifies to 3 equals negative 3a. Dividing by 3, we find that a equals 1. This value is negative, which confirms the graph opens downwards. Now we can write the final equation by substituting a equals 1 back into our factored form. The equation of the quadratic is y equals negative 1 times the quantity x plus 1 times the quantity x minus 3. We successfully found the equation of the quadratic using its intercepts and one other point. Let's consider another type of problem. Our objective is to find the equation of a quadratic when it touches the x-axis at a single point. Here's a graph where the parabola opens upwards and touches the x-axis at the point suppo, 2, 0. In this case, since it only touches the x-axis, the completed square form, specifically the version with h squared, is most efficient. We use the form y equals a times the quantity x minus h squared. The vertex is on the x-axis at x equals h. Here h is 2, so our equation becomes y equals a times x minus 2 all squared. Now we need to find a. Looking at the graph, we can see it passes through the point 0, 8, which is the y-intercept. We substitute these values into our equation. This gives 8 equals a times 0 minus 2 squared, which is a times 4. Solving for a, we find that a equals 2. This is a positive value, which correctly reflects that the parabola opens upwards. Substituting a equals 2 back into our equation, we get the final result. The equation of the quadratic is y equals 2 times the quantity x minus 2 squared. This shows that knowing the vertex, especially when it's on the x-axis, makes finding the equation straightforward. Our objective in this next problem is to find the equation of a quadratic when we know one x-intercept, the y-intercept, and the axis of symmetry. This requires combining a few of our techniques. Here we have a graph with one x-intercept at 2, a y-intercept at 16, and an axis of symmetry at x equals 1. This is a concave down parabola. The first step is to find the other x-intercept, which we can do using the axis of symmetry. The axis of symmetry is x equals 1, and it's 3 units away from the known x-intercept at 2. Because parabolas are symmetric, the other x-intercept must also be 3 units away, but in the other direction. So, the other x-intercept is at 1 plus 3, which is 4. Now we know both x-intercepts at 2 and 4. This means we can use the factored form. Y equals a times x minus -2 times x minus 4. This simplifies to y equals a times the quantity x plus 2 times the quantity x minus 4. The final step, as always, is to find the value of a. The graph shows a y-intercept at 0, 16. Substituting these values into our equation, we get 16 equals a times 2 times -4, which is -8a. Solving for a, we get a equals 2. This confirms the downward shape of the parabola. Substituting a equals 2, our final equation is y equals -2 times the quantity x plus 2 times the quantity x minus 4. This example demonstrates how to find an equation by creatively combining the axis of symmetry and the factored form. Let's explore another common scenario. Our objective is to find the equation of a quadratic when we know its vertex coordinates and one other point. We have an upward opening parabola with a vertex phi at 3 or 2. We are also given a y-intercept at 0, 16. Because we are given the vertex form is the most efficient choice. The vertex form is y equals a times the quantity x minus h squared plus k. We know the vertex is at hk equals 3, 2. Substituting h and k, our equation becomes y equals a times the quantity x minus 3 squared minus 2. Now we need to find the value of a. We use the other point we were given, the y-intercept, 0, 16. Substitute x equals 0 and y equals 16 into our equation. This gives 16 equals a times -3 squared minus 2. Simplifying, we have 16 equals 9a minus 2. Adding 2 to both sides, we get 18 equals 9a. Dividing by 9, we find that a equals 2. Again, the positive value of a matches the upward opening shape of the parabola. Finally, we write the equation by substituting a equals 2 back into the vertex form. The equation is y equals 2 times the quantity x minus 3 squared minus 2. This process is very direct when the vertex is known. Our final learning objective is to use finite differences, which are also known as difference tables, to find quadratic equations from a sequence of y values. This is a powerful technique when you have data points at regular x intervals. Let's consider a general quadratic function y equals x squared plus bx plus c. We can build a table of values and then calculate the differences between consecutive y values. We call this the first differences, or delta 1. The first differences form a linear arithmetic progression. 2a plus b, 4a plus b, 6a plus b, and so on. If we then calculate the differences between these first differences, we get the second differences, or delta 2. The second differences are all constant and equal to 2a. This is the crucial property. If the second differences of a sequence are constant, the sequence can be modeled by a quadratic function, and that constant difference is equal to 2a. The other important observation is that the y-intercept, c, is the value of y when x is 0. And the first difference, a plus b, is the difference between the first and second y values. These three pieces of information, c, a plus b, and 2a, are enough to find a, b, and c. Let's apply the difference table method to find a quadratic from a set of values. Our objective is to determine a quadratic function given its table of values using finite differences. Consider the following table of values. We suspect it might be quadratic, but we need to prove it and find the equation. Step 1 is to create a difference table. We start with the y values. The first row contains our y values. Next, we find the first differences by subtracting consecutive y values. We calculate 5 minus 6 is -1, 8 minus 5 is 3, 15 minus 8 is 7, and 26 minus 15 is 1. These are our first differences. If this were a linear function, the first differences would be constant. They are not, so we proceed to the second differences. We calculate the differences between our first differences. 3 minus -1 is 4, 7 minus 3 is 4, and 11 minus 7 is 4. The second differences are constant. This proves that the function is indeed a quadratic. Now we can find the equation y equals ax squared plus bx plus c. From our table, we can extract three key equations. The y value when x is 0 is the y-intercept, c. So c equals 6. The first-second difference is 4. We know that 2a equals the constant second difference, so 2a equals 4, which means a equals 2. The first difference is -1. We know that a plus b equals the first difference, so a plus b equals -1. Since we know a is 2, we have 2 plus b equals -1, which gives b equals -3. Now we have a, b, and c. We can write the equation of the quadratic as y equals 2 squared minus 3 qualis plus 6. This example showcases the elegance of finite differences for problems with regular x intervals. Let's apply finite differences to a real-world problem. Our objective is to determine a quadratic model from a given scenario and then use it to make a prediction. This problem asks for the maximum number of pieces into which a pizza can be cut with n straight cuts. Let's start with a few cases and record the results. With one cut, we get 2 pieces. With 2 cuts, we can cross them to get a maximum of 4 pieces. With 3 cuts, if we cross them optimally, we get 7 pieces. And with 4 cuts, we can get a maximum of 11 pieces. This is our data set. Let's create a difference table for the number of cuts, n, and the number of pieces, p. The first differences are 2, 3, and 4. They are not constant. The second differences are both 1. Since the second differences are constant, we know the relationship between n and p is quadratic. Now we can find the quadratic equation p equals n squared plus bn plus c. Be careful here. Our table starts at n+1. We must extrapolate back to find the values for n series. Since the second difference is 1, the first difference between n+0 and n+1 must be 1 less than 2, which is 1. The y value at n+0 must be 1 less than the y value at n=1, so it is 2 minus 1, or 1. This means c equals 1. Now we use our standard formulas. 2a equals the second difference, 1, so a is 1 nisas 5. And a plus b equals the first difference, which is 1. So 1/2 plus b equals 1, which means b is 1/2. The equation is p equals 1/2 n squared plus 1/2 n plus 1. We can test it. For n4, p is 1/2 times 16 plus 1/2 times 4 plus 1, which is 8 plus 2 plus 1, which is 5a. It works. Now let's answer a prediction question. How many cuts are needed to get 100 pieces? We set p to 100 in our model. This gives the quadratic equation 100 equals 1/2 n squared plus 1/2 n plus 1. Rearranging and solving this equation, we find that n must be about 13.6. Since we can't make a partial cut, we need 14 cuts to guarantee at least 100 pieces. This shows the practical application of quadratic modeling. Let's work through an IB-style problem to consolidate your understanding. Our objective is to solve a problem that requires analyzing the relationship between 2 quadratic functions. The problem asks for the values of k for which the 2 functions, f of x equals x squared minus 4x plus 3, and g of x equals k times x squared, do not intersect. If they intersect, their y values must be equal at the point of intersection. So, to find their intersection points, we set f of x equal to g of x. This gives the equation x squared minus 4x plus 3 equals kx squared. This looks like a quadratic equation, but it has 2 variables, x and k. To solve for the values of k, we need to rearrange it into the standard form of a quadratic in x, which is ky1 x squared plus 4x minus 3 equals 0. The question is about the functions not intersecting. How can we translate this into mathematics? If the functions do not intersect, it means there is no real value of x that satisfies this quadratic equation. For a quadratic equation to have no real solutions, its discriminant must be negative. This gives us our condition. Let's find the discriminant in terms of k. In our rearranged equation, a equals k minus 1, b equals 4, and c equals 3. So the discriminant is b squared minus 4ac. This is 4 squared minus 4 times the quantity k minus 1 times 3, which simplifies to 16 plus 12 times the quantity k minus 1. The discriminant is 12k plus 4. Now we apply our condition for no intersection. The discriminant must be less than 0. So 12k plus 4 is less than 0. This is a simple linear inequality. Solving for k, we get 12k is less than 4, which means k is less than negative 412, or negative 1/3. We have one final check. What if k equals 1? If k is 1, our original equation, k pawanin x squared plus 4x minus 3 equals 0, becomes a linear equation. 4x minus 3 equals 0. This has exactly one solution. X equals 3, 4. This means when k equals 1, the functions do intersect. So our condition k is less than 1 to 3 is correct. The final answer is all values of k less than negative 1/3. Let's work through another IB-style problem, focusing on using the discriminant to ensure a quadratic expression is always negative. Our objective is to determine a range of values for an unknown coefficient that ensures a quadratic is negative definite. The problem asks for the range of values for p such that the quadratic px squared plus px plus p plus 2 is always negative for all real values of x. This is the definition of a negative definite quadratic. For a quadratic to be negative definite, it must satisfy two conditions. First, the parabola must open downwards. This means the coefficient of x squared, which is p, must be less than 0. Second, it must never touch or cross the x-axis. This means the discriminant must be less than 0. Let's apply the first condition. The coefficient of x squared is p. So our first condition is simply p is less than 0. We'll need to remember this when we combine our results. Now for the second condition, the discriminant. Our coefficients are a equals p, b equals p, and c equals p plus 2. The discriminant delta is b squared minus 4ac. Substituting these, we get p squared minus 4 times the quantity p plus 2. Expanding and simplifying this, we get negative 3p squared minus 8p. We need the discriminant to be less than 0. So negative 3p squared minus 8p must be less than 0. Let's solve this quadratic inequality. We find the roots by setting it equal to 0, which are p equals 0 and p equals negative 8, 3. Since this is a downward opening parabola, the inequality is true when p is less than negative 8, 3, or p is greater than 0. Now we must combine both conditions. Our first condition was p is less than 0. Our second condition is p is less than 8, 3, or p is greater than 0. We need to find the overlap. The values that satisfy both inequalities are pi kit is less than negative 8, 3. This is our final answer. The quadratic will be negative definite if and only if p is in this range.